All right, so we're going to explore a little bit more on the topic of interference. There's a device that you can look at called an interferometer, and as the name implies, it's interference that is measurable. That's literally what interferometer means. And the way this works is it's a device that takes a beam of light and decides to split that beam and later recombine it to produce an interference effect. And from that activity, you could determine very fine scales of distance and time. That's the idea behind an interferometer. Interferometers actually serve a lot of purposes. For example, in astronomy, which is my expertise, interferometers are used to combine signals from multiple telescopes into a single coherent pattern, as if all the telescopes in tandem acted as a single large telescope. That's the essence of an interferometer. Okay. In fact, one of the reasons why interferometers were invented was to try to prove that in the universe there exists what's called an ether. There is a fluid in the universe that everything exists in, which would provide a uniform reference frame for all observations. And one of the reasons why interferometers were made was to test this ether. And nothing came of it because there is no ether, which is a lovely conclusion, worthwhile, you know. All right, so this is your basic what's called Michelson-Morley interferometer. In fact, Michelson and Morley were a pair of physicists that attempted to actually discover this thing that I called ether. And the idea is that it takes a beam of light. Now, let's pay very close attention to what we're looking at here. Take a beam of light that is made up of a single wavelength, because as you know, there's a wavelength dependence to many of these concepts. It enters a piece of glass. It hits a boundary that acts as a beam splitter. And what that means is some of the light is reflected and some of the light is refracted. That's the idea. So some of the light comes straight, some of the light gets through and continues along the normal straight line path. Some of the light gets reflected and heads up in this direction here. Now, these mirrors are constructed in a very special way that you can control the distance of light. Right? So what happens is that when the light reflects through here, there's a path through the glass, path outside of the glass, comes back, refracts through. The same thing occurs in this path here to the right. There is what's called a compensator plate here, because you've got to realize that for the reflected light in the original piece, it goes through glass twice. So to give a proper comparison here, you want your light to go through a piece of glass so that the same change in speed effectively is obeyed. And what happens is those two beams combine together to produce this final beam of light right here. And an observer can look at it. Now, you don't put your eye here, though. The idea is that you post this on a screen of some kind. And any kind of wavelength difference between the two paths would become evident in your picture. So that's the idea behind this. And least from a modern standpoint, one of the benefits of a device like this is it can measure extremely fine differences in distance, very fine differences. Because the idea up here is for M2, this mirror is movable. You can make very slight adjustments. So when I say slight, I mean very slight, microns. Very slight adjustments in the mirror. Because ultimately what you're looking for is that the two beams recombine and produce an interference pattern. And if you make minor adjustments to the beam, you can see a variety of interference patterns, which is kind of neat. Anyway, all right, so you're familiar with interference. The idea is that the path lengths in the interferometer, if the path lengths, now, got to realize what's happening here. The path that the light takes is double these distances because they go back and forth, right? Now, our traditional definition of interference never changes. The path length difference has to be equal to a whole number of wavelengths. Now, when I do my path difference, I divide by the factor of 2 because I'm going back and forth, and I end up with a relationship that's here. But the path length difference between the two beams has got to be a whole number multiple of half the wavelength. It would normally be the wavelength, but it's half because of the nature of the path length difference. And of course, the destructive is the same way. The differences need to be a half integer multiple to make sure that destructive interference occurs. So that's the same stuff, nothing surprising there. Interestingly enough, though, the patterns that you get are circular fringes. That's the idea. Because the beam that comes in is a straight beam, and then there's another beam that interferes with it, and as a result, it takes on the appearance of the aperture. Usually if we have some kind of circular aperture. You don't have to have a circular aperture, by the way. We can choose anything we want, but we happen to choose a circular one, and so as you adjust the distance, the fringes start to shift. And it's unfortunate that we are in pandemic life because we have these devices that we use in lab. And it's something that you have to kind of see in person to really appreciate what you're looking at. No demonstration over video or even in a video really does it justice. So, all right.
Is there any way that like would be better to this medium then, or like I guess what's a better way to experience it now?
Well, the only thing I could think of, and I'll have to dig this up, but if there exists a video that has multiple camera angles, for example, we have these devices in the lab, and if there is a camera or multiple cameras that can view the device, view the patterns, and then view the small shifts in distance, then you can kind of visualize what's going on here. I mean, I'll look for it, to be honest. I mean, tomorrow morning I'll look for a video. I've never come across something, so if something's out there, it's got to be rather new. But there's a lot of things to keep in mind, put it that way. And you have to sort of, if you're going to have a video that displays this effect, you got to have to make sure that you sync all the videos up. A video of the device, a video of the mirror shifting, a video of the circular fringes. All those things would have to be perfectly aligned in time. I never come across anything like that, but I mean, if it exists, I'll find it for you, you know. But anyway, that's why it's challenging.
Okay.
Yeah. All right, so we have an interferometer here. We're using a red light. It produces fringes with the bright spot in the center. Great. If the wavelength of light is doubled, okay, what will happen? What is in particular? What is the center going to do? So think about that for a minute. The answer here is D. We don't really know, actually. So the idea is this: the path length difference, right, is 2 times the distance that a given mirror is. And for constructive interference, that is m lambda. Now, if you double lambda, which is what we're trying to suggest here, double the lambda. It's not perfect, but we're pretty close to doubling it. If m must be half to keep delta L constant. That's true, right? I mean, if you look at the relationship here, if you double lambda, you got a half m in order to keep this thing a constant, which it is, you know. Now, here's the tricky thing about this, though. If the value of m that's needed to keep the delta L over 2 constant, if it's still a whole number, well, you got constructive interference. You're gonna have a dot in the middle. But if you half m because you doubled lambda, it's possible that m originally was an odd number and that m over 2 is a half integer, and that means destructive interference. So we don't know at the moment. In the current picture, we do have a bright fringe in the center, which means constructive interference happens at m1, 2, 3, and so on, and destructive, which would have just a ring. There would be a ring with a hole in the middle. And that's destructive interference, and it would follow the half integers. So we don't quite know in this problem. That's the thing. Because we don't really know how this is connected to like the fundamental wavelengths that exist. It's a little tricky. And then in your responses, I could see that trickiness. All right, first question here. Let's jump to our examples. An experimenter uses an interferometer to measure one of the wavelengths of light emitted by neon atoms. Mirror 2 moves until 10,000 bright central spots have emerged. So one of the things that you see is when you move one of your mirrors, the pattern of rings change. It almost looks like you're zooming in or zooming out, because the fringes, the rings of the fringes kind of start to move very rapidly. And so it can give the appearance of zooming in or zooming out, but you're just experiencing various fringes here. So the mirror has moved a distance of 3.164 millimeters. We want to know what the wavelength of light is. So the idea behind this is the following. We're using the constructive interference relationship because we have bright spots, right? So the change in the order is going to relate to a change in the distance. That's the idea. If you have different orders, you have to do that by having different distances. In this case, delta M is 10,000. So we're going to solve for lambda here. So a distance of 0.003164 millimeters. Got to put it in terms of meters. And the delta M is 10,000. We end up with a wavelength of 633, which is deep red and is consistent with a standard neon laser. So in this problem, what we're doing here is we're looking at delta M's and relate them to delta L's. Jean uses a interferometer with a 606 nanometer light, a krypton lamp. Fine. He displaces the movable mirror from him. He counts 818 fringes. So what happens is when you see that pattern of rings, as you move the mirror, they kind of either expand out or they come in. And the idea is that if they expand out, every time a ring moves, that's a fringe. That's the idea. Lina replaces the krypton lamp with a helium lamp of a different wavelength, and she also counts 818 fringes. What's the distance each person moves the mirror? Obviously, they have to move the mirror different distances if they have, the same fringes for different wavelengths. What's the overall displacement? Let's dig right into it. Okay, here's what Jean does. Jean has a delta M of 818 with a wavelength of 606. So when you put that into the constructive interference equation, we end up with a delta L of 0.248 millimeters, about a quarter of a millimeter. Great. Linda decides to delve into this, and she also discovers 818 fringes with a wavelength of 502. That corresponds to a shorter distance, because you have a shorter wavelength, of 0.502. So if we assume that they did their counting right, and again, we don't have lab, which is unfortunate because one of the things that you experience in lab is a crazy amount of frustration because you got to count these rings. It's not easy to do, actually. It's kind of tough. It's kind of a joke with this problem, but if you don't do it, you don't get it. Anyway, overall displacement, when we subtract these numbers, we get a 4.3 times 10 to the 5th. And that is the difference in distance that these two experience if they're going to see 818 fringes with their wavelengths. It's a small distance, but it does very easily allow you to distinguish between the two. All right, let's delve into the topic of diffraction. Now, diffraction is very similar to interference with a small caveat. And the small caveat is this. Interference depends on two different sources. They can be coherent, but there's clearly two areas of wave generation, and they interfere. And it produces everything we've talked about up to this point. Diffraction is a bit different. Diffraction looks at the interference that occurs among a single source of light. It's possible that light can interfere with itself. And if that happens, that is specifically under the topic of diffraction. And so in the picture that you see here is a great picture of water waves. Now the water waves come in as a plane wave, but when they hit the boundary, only some of the wave is able to get through. Top and the bottoms are blocked, but according to Huygens' principle, when that wave does get through the opening, it is now a creation of its own of independent wavelets, which will expand out from the source. Now, these plane waves are still expanded out from the source, but because they're plane waves, you don't see the expansion. You see the normal progression of the waves. That's the idea. So anyway, the spreading out of these waves, due to having it appear through a thin slit, is what we call diffraction. Very similar ideas. But the big difference is that interference relates to two objects produced in the patterns, whereas diffraction is a single source doing it. So let's look at the details. Okay. Irrelevant. Okay, not sure what any of this stuff means. I already said a lot of the stuff. Yeah. That's the same stuff. I already said this. Oh my goodness, I already said a lot of this stuff. I said this. I said this too. My goodness, I gotta organize my slides a little more apparently. All right, let's look at it. Now, the idea here is you're going through a single slit, right? And so if you're going through a single slit, then you can look at individual points on the slit as producing a pattern of wavelengths, according to Huygens' principle. So you can see in the slit here a single slit of width A, which is how we indicate this. Now, remember for interference, the slit difference was D. The slit width, how wide your slit is equal to A. Now, in this case here, just to be really super clear, we're not looking at multiple slits. We're looking at one thicker slit of slit width A. And what happens is the different points in the slit width produce, a source of wavelets. So it's possible that 2 points along a single slit can produce an interference pattern. So that's kind of like, in a way, it's a little deceptive. We use the word diffraction, and it almost implies that it's different than refraction. That's not the case. Both situations are interference patterns. I said refraction. That's not... Getting my terms mixed up here. Sorry. Interference and diffraction sound like different things. They're not. Interference and diffraction are both interference things. In diffraction, light interferes with itself, and in standard interference, you have two different sources that interact, but they produce the same effects. That's the idea. Okay. Now, this kind of refraction that we're looking at here is called Frenzel diffraction, where we actually look at different sources in the slit and see what kind of patterns their path-length differences produce. Simple enough. Fraunhofer is a little bit different. It's a little stranger, but with Fraunhofer, we have our light source, and we have a lens that causes the pattern to converge. They both produce the diffraction patterns, but here's the difference. In the Frenzel, our screen is far enough away that it's almost like the beams are parallel. In Fraunhofer, we use a lens to simulate that the waves are very distant, where they're actually not very distant. They're actually quite close to each other, but the lens can produce an effect that make it seem like the source is very distant. It's a little bit of a trick, but honestly, for the purposes of this class, there's no difference. I mean, I gotta mention it because in diffraction, these concepts are important, but they really will not affect the work that you do here. I mean, that's the idea. Okay. All right, good. So let's look at the single slit diffraction pattern. So here's the idea. We got a wide slit of width A. The light exits the slit, and just for the example here, we're going to assume that it exits at some angle. It doesn't have to, but it's interesting for the example. Okay. Now, what we're going to consider is half the slit width, like upper half compared to bottom half. And as you can see here, the bottom half is going to have a longer path difference than the top half if they're being directed upward. Because the bottom one has this, and I'll draw it out here for you. Okay, let's draw this. So here's a perpendicular line right here. And if I compare, say, the top portion, which I'm calling ray 1, with ray 2, we have, and it's already drawn here, but I'm just going to emphasize it. We have this extra path length right here. This is, now, the rays here, ray 1 and ray 2, are separated in slit width by exactly A over 2. When we do that, just to be clear, every point on top is paired with a point on the bottom. And that means every point on top can be paired with a point on the bottom that has precisely the wavelength difference indicated here. Right, which is what we're indicating with the sine function, and the path length difference is lambda over 2. That's the idea here, because we have half the width length here. And so, yeah, with a single slit, things can interfere. You don't need two slits. You can have a single slit. Now, of course, this gets more complicated when you combine the two, which we'll look at actually. If we look at a single slit, there's a central maximum that is quite large. Right? There's no path length difference when you go to the center. You get a very strong response there. There are a secondary maximum, which is indicated by the figure here. Now, what we keep track of here, though, is not the bright fringes. We actually want to keep track of the dark fringes. So as you can see here, a p-value of 1, okay, is your first dark fringe, right? First dark fringe. And the angle at which that is displayed is a function of lambda over A. Now, again, here's how it works. This equation looks more like this. Let me draw this out with my A over 2 sine theta. That is, right, A over 2 is your hypotenuse. Sine theta is the angle. And that's got to equal what? Well, it's got to equal the path length difference. Okay, fine. Now, we make some assumptions here. Right? The assumptions are this. When you deal with your path length difference, we're looking at minimums right now. Right? So that's lambdas over 2. So the 2's drop out. Again, go back here. What's the path length difference we're actually considering? We're considering half wavelengths. Because in diffraction, we want to know dark fringes. So the 2's drop out, and then we divide by A, and assuming we have a small angle approximation, which we do, then sine theta just becomes theta, and we end up with this relationship here. Now we're using P instead of M, because M is meant for interference, and P is meant for diffraction, and of course, we're going to blend these two together. We're going to look at situations where we have both. You have both dark fringes and light fringes. That's it. So here's our relationship for the dark fringes. Now here's what's really cool about this. If you double this equation, right? Because this angle right now tells you this. Let me highlight this. This is cool stuff. Okay, if I just have the angle, it defines this distance right here, from the central to the p equals 1. If you double this, you get this distance right here, from the top to the bottom. And you know what that distance is? It's the width of the central maximum, which, as you're going to see at the end of this lecture here, or maybe next week, Wednesday, this coming Wednesday, I don't know how much you're going to get through today, this defines a very interesting quantity. This defines what we call diffraction limits. What kind of detail can you see in your images? Because this is the limit. Right? You may have a pattern of lines, but they'll produce an image. But the finest detail in an image is whatever the width of the central maximum. That's basically it. You'll see more. We're gonna plow through this. You'll see examples. I'm not leaving you totally cold here. All right, how are we doing on time? Good on time. Excellent. All right. So this is what I talked about. This was the concept I just talked about. What is the width of the central maximum? There's a lot of importance about that central maximum because it's an image you're looking at, but it's broken into these pieces. And the largest piece contains the most detail that you would see. That's the idea. So it's the same relationship. If we go back here, look at this. We're solving for A. So we turn A into W. We double this relationship, and we end up with the distance from the slit to the screen is what I'm going to call L. And then the width of the central maximum is 2W, right? It's from here to here. It says W, but we mean 2W, actually. Anyway, we move to here. The idea is that lambda is determined by a tangent function, which if you have a small angle, it's just lambda. But the tangent function is given by the width, which in this case would be width over 2 over L. So we take that relationship and we put it into this equation here. That's how we get the 2 up here. That's how we get the lambda. That's how we get the L. So this is a really nice relationship that communicates how wide that central maximum is, given our wavelength, screen distance, slit width, and everything. It's a little confusing, honestly, because we have W, which is what represents a width, and we have A that represents a width. But the A is the width of the slit, and W is the width of the fringe, which are radically different things, honestly. So anyway. All right. So, question for you here. We have a wavelength of light passes through a single slit of width A. Diffraction pattern is observed. Which of the following will give the greatest increase in the angular width? Ooh. So you got to remember the equation. And if you don't worry. I got it for you. W 2 lambda L over A. What's going to produce the greatest increase in W? Oh, never mind. I do. Yeah, you're right. Let's go back to the equation here. If you lower A, you increase W. If you double lambda, you increase W. Excellent. Great job. Light from a neon laser, 633 nanometers, passes through a narrow slit. The screen distance is 2 meters. The first minimum, when it comes to diffraction, we care about minimums. And the pattern is 1.2 centimeters from the central maximum height of the Y is the slit. All right, so we have our width equation, right? 2 lambda L over A. Got to solve for A. That's the slit width. Put our numbers in here. Nothing tricky about this. Make sure you put in nanometers. You know, we got our distance in meters. Great. Now, I mean, everything's got to be SI, so make sure you convert everything to SI. The 1.2 centimeters, got to put it in meters. Everything's good, and we got a slit width that is seemingly insanely small. 0.11 millimeters. Well, it's small, but when your screen is 2 meters away, you get a pretty significant pattern of lines. So that's the idea. All right, let's look at example 3. Light passes, oops, hit the full screen here. Come on, Zoom, work with me. All right, light passes through a 0.12 millimeter slit, basically the same as the last example. Forms a diffraction pattern on a screen 1 meter away. The width of the central maximum is 0.85 centimeters. What's the wavelength of light? Well, it's the same deal, same equation. Everything applies here. Nothing special. Solve for lambda. Put in our value of A. It's so tiny. Got our omega in there. Not omega. W, sorry. That's the right in meters. Meters for the, yeah, and we got 5, 10 nanometers. All right, cool. Simple enough. All right, let's do this question, and then we'll take a break. We're a little more than halfway through, so I think we could take our break now. Yeah. Okay, so laboratory experiment produces single slit diffraction on a screen if the slit is made narrower. If you could imagine that, the bright fringes will be what? What do you think? Based on the equation. Now, to remind you, right? Lambda, P, not lambda, theta. Theta equals P lambda over A. Let me know what you think. Letter in the chat, yo. All right, so we have our width equation, right? 2 lambda L over A. Got to solve for A. That's the slit width. Put our numbers in here. Nothing tricky about this. Make sure you put in nanometers. You know, we got our distance in meters. Great. Now, I mean, everything's got to be SI, so make sure you convert everything to SI. The 1.2 centimeters, got to put it in meters. Everything's good, and we got a slit width that is seemingly insanely small. 0.11 millimeters. Well, it's small, but when your screen is 2 meters away, you get a pretty significant pattern of lines. So that's the idea. All right, let's look at example 3. Light passes, oops, hit the full screen here. Come on, Zoom, work with me. All right, light passes through a 0.12 millimeter slit, basically the same as the last example. Forms a diffraction pattern on a screen 1 meter away. The width of the central maximum is 0.85 centimeters. What's the wavelength of light? Well, it's the same deal, same equation. Everything applies here. Nothing special. Solve for lambda. Put in our value of A. It's so tiny. Got our omega in there. Not omega. W, sorry. That's the right in meters. Meters for the, yeah, and we got 5, 10 nanometers. All right, cool. Simple enough. All right, let's do this question, and then we'll take a break. We're a little more than halfway through, so I think we could take our break now. Yeah. Okay, so laboratory experiment produces single slit diffraction on a screen if the slit is made narrower. If you could imagine that, the bright fringes will be what? What do you think? Based on the equation. Now, to remind you, right? Lambda, P, not lambda, theta. Theta equals P lambda over A. Let me know what you think. Letter in the chat, yo. C's? What? It's C, I'm just joking. All right. Yeah, they're going to be farther apart because guess what we're doing here? We're going to lower A, right? If the slit is made narrower, lower in A. If we lower A, now, realize what I did here though, right? Now, the equation's this. Let me just be really clear about this because you saw this back in interference as well. Theta. Theta are the angles at which things occur. P lambda over A. But a lot of times we really care about not just theta, but if we know the screen distance, we can know exactly how displaced those things are. So we swap this with y over L. And that's an approximation for theta, P lambda over A. And so we solve for y, and we get the relationship you see right here. If you lower A, you will increase P. Now, here's where it gets cool. Here's where it gets cool. We have diffraction. No, think about the stuff we did last class, right? We had interference from double slit experiments. Great. We dealt with that. That looks like the stuff down here, right? But guess what? You have diffraction that occurs on individual slits. So ultimately, what you're going to look at is a superposition of both ideas. And that is the more realistic picture of the two-slit experiment. Now, I didn't tell you that. Way back when Young did his stuff, you saw a lot more than just interference. You saw other things. I didn't tell you that because I didn't want your brain to explode. But now it's okay that your brain explodes. But when you have a two-slit interference pattern, you don't. You have your two-slit interference pattern that is encased in an envelope. Here's your envelope. Your double-slit interference pattern is encased in an envelope that is dictated by diffraction. And so you get this beautiful picture up here. Look at this picture. You have an interference pattern that with an envelope of diffraction. So normally you would get this sort of infinite series of slits here. But imagine that that was embedded in the diffraction pattern. And that's how most diffraction patterns and interference patterns work. This is the more realistic picture. So check out this picture down here, this photograph. This photograph shows a lot of central fringes. Those are all embedded in the diffraction maximum. It's hard to see here, but the patterns of fringes do continue to the left and to the right, but the intensity of that light is incredibly low. So it becomes very difficult to see that kind of pattern here. Okay? In the particular example that we're looking at, it just so happens that the distance between the slits is 4 times the slit width. And if that's the case, then you have this pattern that you see down here. 1, 2, 3, 4. 1, 2, 3, 4 on either sides. And then you get your diffraction minimums. And the pattern repeats, but it becomes much less profound as you go out from that. This is cool stuff. This makes tons of sense. This is neat stuff. It actually is shocking in some ways that physicists didn't stumble upon this sooner. I mean, it kind of blew me away that the Young experiment was 1801. That's nuts, because a lot of the behavior here was thoroughly investigated decades later. In fact, you want to know something crazy? Check this out. See this stuff that we have here? This is for light. But you know what is crazy that happened about 100 years ago? Is physicists decided to not use light for this experiment. They said, you know what? We're going to shoot electrons through the slits. And we'll see what happens. And guess what happens? If you shoot electrons through the slits, you get the exact same pattern, which establishes that electrons can behave as waves. That's crazy. I mean, that's like mind-blowingly crazy. That it can be light, or it could be particles with mass, and they will still do the same thing. I mean, like, half of me is like, nature, calm down. Anyway, all right, question for you here. A laboratory experiment produces a double slit interference pattern. If the left slit is blocked, let me know what you think happens. So we got this diffraction pattern, beautiful interference fringes. We're going to block out the left-hand side. What do you think's going to happen here? What do you think's happening here? The letter in the chat. This is fun stuff. You know, as you're thinking about this, let me tell you, one of the best ways to study this material is from a historical standpoint. Like, to really look at how, physicists of the day tried to like the most brilliant physicists of the day try to tackle these ideas is pretty darn cool. Like, the amount of physics done. I mean, think about this. 1900 to 1920, like basically that period of time, which is not incredibly long, right? 20 years. Most people can remember 20 years, right? I mean, in that 20-year period, we discovered atoms, electrons, the fact that material particles have wave-like properties, quantum mechanics. I mean, don't get me started on astronomy stuff. It's pretty astonishing. All right, everybody's saying C. It's not C, it's D. Here's what happens here. If you selected C, you're basically selecting the same pattern but a little fainter. There's a problem there. The pattern that you should see here is a diffraction pattern that's an envelope, diffraction pattern that is the envelope of an interference pattern. So, that being said, if you block the left-hand side, the interference pattern disappears and you only have the diffraction pattern. And maybe it's a little bit hard to see in the image here, but the diffraction pattern is, as the fringes get farther away, they gradually decrease. Not substantially decrease, just gradually decrease. And so that's consistent with D. C, the problem with C is that you have the same patterns, but they're a little fainter. Now, the little fainter is true, but you will not see the same space if you don't have interference. Okay, that's the difference. Okay, check this one out. This is the stuff you see in lab. Single slit diffraction, 0.055 millimeter width. We got these fringes here. We got a central maximum, followed by our minimums. The P equals 1 maximums, the P equals 2 maximums. If you throw in a secondary slit, you get the same patterns, but now we have fringes embedded in them. We still have minimums, right? Let me highlight these. Minimums are here, 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 here. But among the major fringes, they're split up among the smaller fringes from interference. Now, if you know how the diffraction and the interference are behaving, then you could define what are called missing orders. This is revisiting interference patterns and realizing that due to diffraction, there are certain patterns in the interference that will be missing. And the way we deal with that is we simply look at the two relationships. Here, the missing interference fringes are given by a ratio of D to A. Remember, D is the spacing between slits, and A is the slit width. And that largely determines the wider pattern here. But there's missing fringes when these two quantities coincide. So, in other words, the initial diffraction destructive interference occurs at P, which is apparently at 6 and at 6. And we have these interference patterns. Fine, it looks like the ratio of D to A here, just to be clear, looks like it's 6 to 1. Right? Because the first missing order happens at a diffraction minimum. So 6 to the left, 6 to the right, in this example, D to A is a factor of 6. All right, we have a 500 nanometer laser light. Lovely. Illuminates a double slit pattern. Ooh, it produced an interference pattern on a screen that is 90 centimeters away. Excellent. Good information. The bright bands are 1 centimeter apart. That's the Y values. The third bright bands on either side of the central maximum are missing. Ah, that's our missing orders. Check it out. Check this out. The missing orders are number 3. And that has to equal PD over A. Nice stuff. Got our wavelength. Got our screen distance here. What do we want to find? The width and the separation of the two slits. Let's deal with interference first. Interference first is going to have this equation that we're all familiar with. D sine theta, m lambda. Sine theta is like a tangent, which is y over L. We solve for D. We get a distance between the slits is 4.5 times 10 to the minus 5. Excellent. We want to find the width. That means we need to find A. We know our missing fringe pattern is 3. Of course, that means if we're missing the pattern at 3, that means that is the first diffraction minimum. So that means P is 1. Solve for A. P is 1. M is 3. D over 3. 1.15 times 10 to the minus 5. Excellent. Excellent. What if we don't have 2 slits? What if you have 3 or 4 or 5 or 1,000? What happens then? Well, you have interference from multiple slits now. And the same thing applies, right? If you got 2 slits, you're interested in the small separation that corresponds to the distance between the slits. But if you have a second slit after that one with a 2D distance, that's going to behave the patterns too. If we have a third slit, sorry, a fourth slit, that's going to be 3D sine theta. And a fifth slit is 4D sine theta. They're all going to behave the patterns. All right, so if you have 2 slits, that is indicated by the purple here. I'm not a fan of this purple. It's a little too dark for me. I like my purples to be a little softer on the eyes, and I apologize for that. Let me put some softer purple for you. You know what? And when I do this, it's not purple anymore. It's lavender. So let me do this. All right, this is normal interference. Okay, I knew I drew that like I was 4 years old. Sorry, I'm not so good at the hand. Okay, I'm so sorry. I'm trying here. Anyway, the 2 slits produce really simple patterns, right? Maximum, minimum, maximum, minimum. Easy peasy, right? But here's where it gets a little tricky. Let me clear this out for you. 3 slits. What do 3 slits do? Well, when all 3 combine together, you get this more intense region. It's a red. I'll go with a red. I'm not a big fan of red. I don't like red. I play Magic the Gathering. And, you know, mono red just makes you want to throw up. That's just my opinion. If you play Magic, maybe you agree, maybe you don't. But anyway, there's our 3 slit pattern. What's going on here? A more intense maximum. And then we got these minimums here. What are these minimums? Guess what? It's when only 2 of the slits interfere. And they produce the little minimums. But when all 3 slits appear, you get this beautiful big jump in intensity. Lovely. What about 4 slits? Glad you asked. Let's go to the blue. I'll go for a lighter blue here, a little baby blue. Ooh, that's a beautiful blue. Now we get a big, huge intensity jump. Then we get these little jumps here. What are the little jumps? The little jumps are when two slits interfere. We get these little jumps here. But when all four slits interfere, we get a big jump here. And you can probably predict what happens subsequently. 5 slits, 6, 7, and so on produce little tiny maximums and a gigantic, maximum when all of them combine. That's the idea behind this idea. So this happens to be the pattern for an 8 slit gradient here. So interference, we have a screen with 8 slits on it. And you can see what happens here is we get these little tiny maximums. We got a big one here. 1, 2, 3, 4, 5, 6, 7. Okay, so from a big one here, 1, 2, 3, 4, 5, 6, 7. N minus 1 maximums. Why n minus 1? Because you have to have an interaction, right? How many interactions can you have? Well, one has to interact with another one, so you can only have 7 of them, right? We get this big, huge peak here. And it turns out, and I didn't really explain this earlier on because it kind of involves a lot of electricity and magnetism, which you're not technically supposed to have. So I didn't include it. But I will tell you this. For this kind of patterns here, the number of slits squared gives you the intensity of these maximums here. And these maximums occur when all slits work together and combine and give you a maximum there. That's the idea. This is for 16. I mean, you can see the patterns here. The centrals become enormously huge. There is still these secondary patterns, but they're so small because you have one or you have 2 or 3 things interfering and that's it. It doesn't compare when you have all 16 together. You get this enormous jump here. That's pretty cool. All right, so let's look at a problem that involves, see how we navigate doing these things. We got 10 slits, equally spaced, 1/4 millimeter apart, and illuminated with yellow light of wavelength 580. We want to know a lot of things about this. Now, just to let you know where we're going with this is a 16 slit pattern. I mean, this is baby stuff, right? And I know I keep saying this, and I probably should just shut my mouth, but things are so much nicer when we have lab, because you can see all these things. We have diffraction, interference patterns that will give you thousands of slits per millimeter. Thousands. And the patterns that are produced are, extreme compared to this. That's the last time I'll mention how much nicer it is to study physics outside of pandemic versus in pandemic. Sorry about that. All right, let's look at our 10 slit pattern here. What are the angular positions of the 3rd and 4th principal maximum? Easy peasy. This is just your general interference relationships. Doesn't involve the number of slits. No. This first question is all about how does interference happen? You don't have to know how many slits there are. And I plug in 3, and I plug in 4. Those are my order numbers, and I get out these various angles here. Great, fine. What is the separation of these maximum on a screen that's 2 meters away? Okay. Now I can take my angle and express it as y over L. Remember, sine theta is the same as tan theta, which is the same as theta, if your angles are sufficiently small. And guess what? These angles are sufficiently small. So we'll work at my delta y. And the distance between these, which will be given by the difference in the sine angles here, which is just the difference of the angles, 4.6 millimeters. That's it. Now, I didn't need to incorporate the 10 yet. However, if I wanted to know that, the intensity of the light would be 100 times larger than normal because there are 10 slits doing exactly what you see in my problem here. I analyze 2 slits working together. But imagine you analyze 10 of them working together. The physics all the way up to this point right here are the same. All the physics from here down are identical regardless of slits. What is the 10 used for? Well, at least at this point, it's used to express intensity. So when you do find those fringes, they're enormous. They're absolutely insanely large. They are apparently 100 times, right, the normal fringe. Now, look, I said fringe width, approximately 1/10. What does that mean? It means if you want to study the little fringes, right, if you divide this number 4.6 millimeters by 10, you can get the approximation of where all the little slits occur. Anyway, all right, we got our Young experiment. Now, if we say Young experiment, the implication is it's a 2-slit interference pattern, right? Coherent light passes through 2 slits separated by a distance d. That's redundant. Produce a pattern of dark and bright fringes. Awesome. Complete the sentence. If you instead use 10 slits, each the same distance from its neighbor, is that grammatically correct? Maybe, but that sounds terrible. That's a terrible sentence. If instead you use 10 slits, each the same. I don't care if it's grammatically correct. I'm cringing at this. I mean, let me know. Each the same distance, if instead you use 10 slits, each the same distance d from its neighbor, maybe. I'm not a fan of that sentence. The space between bright areas will blank and the width. Okay, so let's I'm not I'm not your English instructor, so please ignore the fact that I may come off as illiterate. Sorry. What do you think is going to happen here, though? 10 slits instead of 2. What happens to the spacing and the width here? What do you think? Let's look at this question here. If you increase, if you say use 10 slits, each the same distance, okay, the spacing, right, will not change, right? Spacing won't change because ultimately you're still dealing with the same interference pattern. But the widths, that's the thing, is that when you include all those other maximums and therefore minimums, you're going to dramatically sharpen up. I like to use that word, sharpen up the maximums. Let's go back. Let's look at this picture here. Hey, look at this. These peaks are, again, I like to use this language here. Maybe you can communicate with this language, but I like to refer to these peaks as being sharper. What do I mean by sharper? They're not very thick. Why? Because you have all these maximums and minimums in between, which involve interactions for individual slits. So what happens is as you increase the number of slits, your central maximum becomes sharper. And so ultimately the spacing is not going to change. The spacing is determined by interference, but the sharpness is determined by diffraction to a large extent. And so the distance between the peaks are the same, but the widths themselves become sharper, which means they decrease, right? Okay, here we go. 8 slits separated by 0.149 millimeters. That is the value of D. It's uniformly illuminated by a monochromatic light of 523. Okay, good. What is the width of the central principal maximum on a screen that is 2.3 meters away? Here we go. All right, we start with our interference pattern. D sin theta, m lambda. we want to change our sine theta to incorporate the screen distance. So it's y or L. Solve for y right here. What's m? Well, we have to, if we're dealing with the fringes here, 8 slits equally separated by this number here. So our value for m is divide by 8 to get the distance to the first minimum. Now that's what I decided to do here. Double to get the width of the fringe. So what did I do? I took my I got my lambda here, I got my L, I'm worried about my D here. The D that I'm working with here is based on the width. The idea here is this. If I want to know the width of the central maximum, then I have to consider what the complete destructive interference is on either side. I'm going to choose an m value of 1, okay, and realize that my width here, 2.06. So if I put that into the formula here, so y is, now m is going to be 1 here. I'm going to consider what one fringe does, because the first fringe, there could be a lot of fringes, right? 8 slits is going to produce a lot of maximum. But here's the thing. It doesn't matter how many slits there are. The very first minimum defines the width of the maximum. So I'm choosing m to be 1 because I want to get to the first minimum. That's the idea. What is my lambda? My lambda is my lambda, so it's going to be 523 times 10 to the minus 9. That's 9. What's L? 2.35. And I'm going to divide that by my 0.10 to the minus 3 because it's in millimeters, not meters. Sorry about that. So it's 1,523 times 10 to the minus 9, 2.35 divided by 0.149 times 10 to the minus 3 because we got to convert things to meters. I end up with a 8.25 times 10 to the minus 6, which indicates the actual vertical distance in this equation here. Now the E wasn't too important. That's the idea. Is that the width of the central principal maximum is going to be determined by, basically where the first minimum occurs. That's the idea here. So I use the wavelength, I use the screen distance, I use separation, and that will get me directly what that distance is. Okay, so